what we have done till now. First tell me how we figured out the actions. We did it this way. So you are having a particle. Let's consider simple single particle. Okay, of mass m. Okay, it carries some charge E, or let's say charge Q for the time being. Okay, so without any electromagnetic field, we figured out its action. Is it? It's simply a free particle, and we calculated what is the action for this free particle. Then we considered this particle to be in this electromagnetic field. Okay, so there we considered this electromagnetic field to be represented by A mu. Okay, and we considered actually the interaction between this charge and field. Okay, so we calculated the simple let's say S1 that corresponds to this particle. Then we consider this S interaction, that is the interaction between the particle and the field. And now there is another part which we have not done yet, that is the action for the EM field itself. Okay, what is the action for this EM field? Consider only the EM field. There are no particles, there are no interactions at all. That means the entire electromagnetic field, free field. Okay, got it? So if I need to figure out the action for an electromagnetic field, so that action should depend upon the properties of field itself. Okay, clear? What we'll look what kind of property is that. Okay, so before going into detail this action, we'll revise certain things regarding these electromagnetic fields. The first property, let's look at the first property of this field. Okay, so the first property which we are going to do here is the principle of superposition. Electromagnetic fields obey law of superposition principle. Okay, so we are having so what does that mean? Let's consider what does that mean? What superposition principle means? Any idea? Yes. Okay. So that means if you are having an equation of motion at hand for, let's say, an electromagnetic field, okay, you consider one solution. If it admits many possible solutions, the linear sum of all these solutions is again a solution to that very wave equation. Okay, so that is the superposition principle. Okay, now let's consider the electrostatic field itself. Let's look how the superposition looks like. Let's say simple electrostatic field. Okay, so you are having, okay, let's say you are having the bunch of charges in this very region. Okay, and you try to calculate the field at this very point P. Okay, clear? So what the superposition principle means? Okay, that anybody? Just one? Yes. That's it? Yes, better. So if I need to figure out the electric field at this point, due to all these charges, how I can do it? Somewhat. Yes, make precise statement. You calculate electric field due to every individual charge at this point. Okay. So you take the sum of all the vectors at this point. Okay. You draw all the possible vectors to this very point and calculate their sum. Okay. That gives you the superposition of the electric field at a given point. The same thing follows if you have the potential. So you can calculate the potential at a point P. So it will be the sum of the potentials due to all these individual charges. Clear? Okay, so now what kind of differential equations I need to have this kind of principle? Okay, what kind of differential equations? Because we know equations of motions are usually defined in terms of certain differential equations. Clear? Look at the Newton's law. You are having that as a differential equation, a basic differential equation. Okay, Now let's look what kind of differential equations I am having at hand, okay, which can yield me this kind of principle, this superposition principle. So I need linear differential equations. Clear? Is that true? So if I am having linear differential equations, their solutions gives rise to the superposition principle. You cannot have non-linear differential equations; they can give rise to the superposition. Okay? So okay, what are those? Okay, from this very principle, I can handle linear. I need linear differential equations. Okay, of. Okay, what are those? It is Maxwell who put all these equations before you. What are those equations? Just tell me what are the differential equations which govern the electromagnetic field? Okay, first equation is the Gauss law, is it? For electrostatics, huh? What is that? So if you consider, let's say, okay, if you are having some charge density rho, you can calculate, okay, so you can calculate the charge Q from this charge density integrating over certain volume, okay. This rho is the charge density and Q is the charge contained in certain volume V, okay. Then you can define, then you are having this equation del dot E is equal to 4 pi rho. Okay, we are in electrostatics units, that's why there is 4 pi, so there is no epsilon naught. Okay, so what does it give me? So over a closed surface, so this is actually the flux, okay, so this is a flux through a surface, that's considered a surface. Inside this very surface is a charge Q, okay, so what is the flux through this very surface? Okay, that means direct lines of force that are coming out of this very surface are moving inside the surface depending upon the nature of charge here, so that is given is proportional to actually this charge, okay. So this is the first law. Now you see, so because of this thing, if it would have been a nonlinear differential equation, then you cannot calculate the fields individually, okay, and then sum up. Okay, second thing is, okay, the same thing, Gauss law, but that is for magnetostatics. So what is that? So it is del dot B is equal to 0, or so you are having over surface. What is the interpretation of this very law? So there are no magnetic monopoles, huh? Okay, magnetic monopoles do not exist, huh? Okay. So it means the total flux emerging from a given surface S, okay, so that's equal to 0. So it means you are having the lines of force, okay, let's say if you are having this kind of surface S, so let's say if you are having a line of force coming here, so it will move back, huh? Okay, so it comes and closes, huh? That's why it does not appear outside the surface. Clear? Or you can think, let's say if you are having a line of force, so the number of lines that are moving out, those are the same as coming out, okay. So that's why there will be flux is equal to 0. Clear? Okay. Now, so it means you don't have actually the monopole, like you are having a monopole here. So this is an electric monopole, that means a single charge. Okay, what is the third equation? Okay, tell me. What is the third equation known as? Yes? Faraday's law, okay? What is that? What is Faraday's law? Faraday's law states what? So you are having a changing magnetic field that gives rise to the electric field. Or in other words, the flux, if you are having a closed circuit, the flux that is changing through that very circuit, that gives rise to the EMF. Okay, and induced EMF exists, okay, if you are having a changing flux. So how we write that? So you are having curl of E, that's equal to minus 1 by C, and the direction of the EMF is given actually opposite to the change. Okay, so it's like this. So E dot dl. So this is over a closed loop. Okay, this integral is over a loop, because you can convert this curl into actually the loop. Got it? What kind of theorem is that? Stokes theorem. Okay, so it's minus 1 by C partial phi by partial. So this is the magnetic flux, and this is the circulation in the loop, and this circulation. Okay, so this is circulation, and we call circulation of E. Yeah? Okay, we call this as EMF, electromotive force. It's not the force. Historically, it has been called force, but it's not the force. Okay. Okay, so what is the fourth law? Anybody? So you are having Ampere, Maxwell's law. So what it states? So here you are having the changing magnetic field gives rise to the electric field. Okay. Now Ampere Maxwell's law is, if you are having a changing electric field, it gives rise to the magnetic field. Okay. So it's like this thing: del cross B is equal to 1 by C. Okay, so this is the current density. Okay, so in the integral form, so it is the circulation of the magnetic field, B dot dl. So this is now the circulation of the magnetic field. Clear? So this I can write 4 pi by C integral over surface. Okay, like this thing, vector J plus 1 by 4 pi partial A by partial T, and this objective. Okay, so this objective is known as displacement current. Rather than Maxwell's displacement current. Okay? Clear? Okay, now if you look at all these equations, so they are linear differential equations. Okay? And first order is actually E. E and B, is it? So are they second order or first order? They are all the first order differential equations. Now we know, if I know what an action, okay, what the form of the action is, from an action I can derive what? I can derive the equation of motion. Okay, let's assume I know the action for an electromagnetic field. Okay, from that action I should be able to derive all these four equations. Clear? And these four equations are actually linear first order differential equations. Clear? So tell me, if I know the action, in that action, okay, what should be these fields? I mean, should these electric and magnetic fields appear as linear terms, or should they appear as the quadratic terms, or should they appear as the higher power terms in the action? Now look here, the structure of these very equations. E and B appear as first order, is it? So do you have any higher order terms? No. So because I derive each term from the action, so in action what order I need? No, I need quadratic order, is it? Because I am varying the fields, is it? Okay. So that means the action must contain these electric and magnetic fields as quadratic forms. Clear? You got my point. So in a given action for the electromagnetic field, they should not be linear order. Clear? Because if I then vary, let's form a differential equation from the action. Okay, let me write it. Okay, suppose, okay, so let's write the action for EM field. Okay, let's suppose if they are, okay, we will guess what kind of action, what kind of terms I need here. Clear? Let's guess. Okay, if they are simply, let's say linear order terms, alpha plus beta p, let's see. Okay, you got my point?
okay, I can make a scalar. Somehow, let's dot it with some another kind of thing. Okay, so now vary action. First, let's vary action. What will happen? I am varying action with respect to fields. So what I will get? I will simply get the constant terms, is it? So because what this will give me? Just tell me. Just tell me what it will give me. If I, okay, delta S is equal to 0, I am varying with respect to E and B, okay? Clear? So that means I need to differentiate this thing. Clear? So it will give me something alpha, relation between alpha and beta. There will be no what? Electric and magnetic field. But what I require? An equation for electric and magnetic fields. Clear? So that means this kind of action which contains linear order terms of E and B is not suitable for electromagnetic field. Clear? So what I need? I need something which contains what? Okay, let's say some function of E square and B square. Once I vary these things, I will get at least E and B, is it? Okay, once you differentiate it, you differentiate a quadratic term, what you will get? You get a linear term. So that is what I mean by that. Okay? So that means the action for an electromagnetic field, what I am looking, it should contain quadratic term, it should be quadratic in E and B, or it should be quadratic in what? Fields. Simply. Clear? So this is the first point. Now the second point is that, so what should be the second point? The action should be Lorentz invariant. Clear? Because I need a action should be a scalar quantity. Is that true? When I say Lorentz invariant, it means it's a scalar and Lorentz transformations. Clear? And second thing, it should be what? What is spell? G-A-U-G. Is this the spelling? Just look. Okay, it should be invariant under what? Gauge transformations. Clear? And it should be a true scalar. Lorentz invariant. It should be actually a true scalar. It should not be a pseudo scalar. Clear? Now anybody remembers, we have arrived at this kind of form if you look. So the quantity which has all these properties is this very object, F mu nu, F mu nu. Okay? So what was this equal to? Anybody? B square minus 2 times B square minus E square. So this object is what? Okay, now if you see, this is quadratic in fields. Clear? This is Lorentz invariant, we have shown in the last lecture. Okay, it is true scalar. Okay, it is also gauge invariant. So that means all the properties what we require for the action for an electromagnetic field are satisfied with this very quantity. So that means the action must be proportional to this very object. Clear? The way we started with the action for a free particle, then the action for an interaction between free particle and electromagnetic field, now we are arriving at the action for the EM field. Clear? Any question? Have you got it? Understood? Clear. Okay. Now how to write the action? Okay, for the EM field. Okay. So for that, what I will do, let me introduce a quantity, what we call as Lagrangian density. Okay, so you will appreciate it in a moment why we require Lagrangian density. Okay, so Lagrangian density I write as this way. Okay, let's write Lagrangian density L. Okay, I write it in such a way that if I integrate this Lagrangian density over volume, I will get Lagrangian. Okay, so let's say if you are integrating the density, what you will get? The quantity back. Okay, let's say if you are in charge density rho, you integrate this over volume. Clear? What you will get? Charge. This is how we introduce densities. Clear? So if you are having, let's say, mass density, Okay, let's call mu to be the mass density, and you integrate over volume, what you will get? Mass. Got it? So similarly, I am introducing a Lagrangian density, which we will be calling as the Lagrangian itself. Okay. So, but for the time being, I will call this as a Lagrangian density in such a way that if I integrate it over volume, I will get Lagrangian back. Clear? So, Samajhan? Okay. So now let's write the action. If I am having now action S, so this action we usually write dTL. Is it? Clear? Okay. So then I can write this dt. What is L in terms of Lagrangian density? d3 of x L. Clear? Okay. So if I multiply, okay, now I know, let's multiply this dt by c like this thing. Okay, I am having this c dt d3x and L. Can anybody tell me what this object is? It's now a volume element in 4-dimensional space, is it? So this is a volume element in 3-dimensional space. You multiply now the length, temporal length, is it? What it will give me? A 4-dimensional volume element. Like this. Clear? Okay, what is this d4 of x? So d4 of x, you write c dt d3 of x. Okay, let's write in Cartesian coordinate system. So it will be c dt dx dy dz. Okay? Now if you see, this very object is invariant under Lorentz transformation. This object, this volume element in 4 dimensions. Okay? So this is invariant under Lorentz transformations. Okay, so show it. So show it. If you have not come across this kind of term anywhere, so show it. It is invariant under what? Lorentz transform. You take the usual Lorentz transform what you are having at hand, the boost along the x direction, then substitute for dt, dx, dy and dz and multiply all the 4 terms, what you will arrive. So in the primate coordinate system, it will be same as in the unprimate coordinate system. The form will be same. That means it is Lorentz invariant quantity. That's why I have put it in terms of actually in the density, so that the measure of integration is a Lorentz invariant quantity. Clear? So this way it is easier to generalize this very objective. We can easily generalize to higher dimensions. Okay, let's say, okay, we can introduce a measure like this thing. We can say, let's write dd, okay, d plus 1. 1 means with for the time, okay, so L. Clear? So it is, from here, it is easy to generalize in the higher dimensions. While here, d dimensions are space dimensions and 1 is time dimensions. Okay, let's write, okay, this d plus 1x, it means actually, let's say c dt, time dimension, another is d dx, so that's c dt, okay, dx, dy, so on. Let's see this way, dx1, dx2, dxt. Clear? You got my point? And this again what? Invariant under Lorentz transformations. Clear? Got it? Okay. So now let's write, okay. So we write now the action for, okay. So what I choose now, the Lagrangian? Okay. Now tell me. So I write Lagrange, okay, this action for EM field to be, okay, let me introduce a constant so that we can match the dimensions like this way. Okay, so let me write it 16 pi c integration over volume d4 of x, so f mu. Okay, now this so this objective form is what? What is our Lagrangian density? Anybody? So Lagrangian density here is -1 by 16 pi c. Okay, so these are simply to match the units. This is a number. Okay, from here you can arrive at the Maxwell's equation, all these 4 Maxwell's equations. Okay, okay, you can choose, let's say, a constant alpha here. Okay, Once you arrive at the Maxwell's equations, you can, from comparing with the Maxwell's equation what you are having at hand, you can actually get the value of this very constant. Clear? So we write this constant. In other words, this is a constant to match the electrostatic units, because we are in our course we have used electrostatics unit throughout. Clear? So this is the Lagrangian density. Any question? Any question till now? Can you turn on the ACs, please? So it's hot. So now let's write what is our the action what we know till this. So we are having, let's say, total action. So total action is due to the particles, let's say. So plane without field, then you are having interaction, okay, then you are having electromagnetic field. So this is also known to us, this is also known to us, this is also known to us. So I will write this SI, okay. So the interaction between the field, how it is written as minus E by C integral A mu dx. Clear? Is this the way? Is this the action for the interaction of a particle with the electromagnetic field? Huh? Is it? Okay, so now what I will, okay, here if you see I have written this very action in 4-dimensional space or some volume. Let's write some volume omega. Omega is a volume over which we are integrating. Clear? So if you see this is over a line, this is a line integral. So this is an integration over dx, that means the world line. Huh? Okay, so what I will do, I will convert this very integral into a 4-dimensional integral. Okay? You got my point? The way I am integrating over d4 of x in certain volume omega, and I will convert this very object into the same form. Clear? For that matter, okay, I need to introduce what is called as the current density. Okay, 4-dimensional current density. Okay, let's do it. Okay, let's try. Let's do it step by step. Okay, so if I am having charge Q, what is the nature of, is this charge a scalar, vector, any other quantity? It's a scalar quantity. Under Lorentz transformations, it remains same, invariant, okay? So that means it's a Lorentz scalar. Eh? If you move from one frame to the another frame, charge, total charge of the system remains same. Clear? Now what about this density? So this is total charge. So this is density. What about this density? Charge density. What will happen if I make a Lorentz transformation? What will happen to it? Density, okay, so you can think total charge divided by total volume, is it? So that gives the density. Tell me what will happen. Because volume is changing under Lorentz transformation, that means density will also change under Lorentz transformation. Clear? So that means this is not a scalar quantity. Eh? This will be, okay, this will change if you make a Lorentz transformations. Clear? Now if I write this very object, rho into dV, what this will give me? Huh? It gives me the amount of charge in volume element dV, is it? So let's call that as, let's write for some, okay, dq. Clear? So what this will give me? So this object is an invariant quantity, is it? Because this will give me the amount of charge in small volume element dV, okay? And this object is what? Invariant under Lorentz transformation. Okay? Okay, so let's proceed. Now, okay, if you are having a charge density rho somewhere, okay, let's say if you are having some region defined by some charge density rho. Okay, you can approximate the charge within the volume as the point charges. So you can be having large number of point charges at certain points. Okay, so this distribution of charge you can think as, let's say, consider a charge distribution with density rho, volume density rho, and all these, you are having all these as what? Charges. Huh? You can consider at each point as a point charge. Is it? And then you sum up, you will get the total charge. Clear? Okay, let's say you are having some position, Ri is the position vector of ith charge. That's right. Qi is the ith charge and its position vector with respect to some origin is Ri. Okay? Now tell me how I can write the density of this point charge. Let's say if you are having at some point R, you are having charge Q. Okay, at some point R. How I write the charge density of this point charge? Okay, so you write this in this way. Okay, let's write some charge density of a point charge. So you'll write, multiply it with the delta of R. So what it will, okay, let's write some R minus R1. Let's write some R minus R0. Let me put Q0. Q0 is the charge where? At R0. Clear? So this will give me the density of the point charge at a given point R0. Okay? Samajh? You know the Dirac delta function? Okay, so let me write a Dirac delta function. So delta of x, so this is defined this way. It is infinity when x is equal to 0, it's equal to 0 when x is not equal to 0. So it is, okay, supplemented by this very condition, the area under this very curve. Okay, so this is how we define the Dirac delta function. It's equal to identity. Clear? So it is something, let's say at x equal to 0, so this at x equal to 0, you can think it as a spike, okay, as a singularity here. But how you can do, you just approximate it by certain function with in the neighborhood of this very point, like this way. So you can approximate this by certain function such that the area under this very curve is what? Identity. Clear? Got it? This is how we define the Dirac delta function. Now tell me, what are the dimensions of this delta of x? In one dimension delta of x, this behaves as 1 by length. Okay? How it behaves? So that's why if you are having, let's say, delta of R minus R naught, so it will give me charge by, let's say if you are having linear charge, delta of x, if you multiply charge by the delta of x, one dimension, it will give me the linear charge density. Okay, if you multiply it by, let's say, three-dimensional Dirac delta function, it will give you the volume charge density. Clear? So it means the charge is located where? When R is equal to R naught, you will be having a charge there. Okay, for R is not equal to R naught, you don't have a charge. So because we have assumed charge to be where? At some point R naught. Clear? Samajh aawa? Okay. So now let's write the total charge density. If I am considering all, okay, I can write the total charge density. Okay, let's say you approximate this distribution by point charges. Okay, let's, okay, Qi. So you'll write all, okay, let's assume the charges are located at certain points Ri. Okay, so you'll write this way. This is a three-dimensional Dirac delta function, so that it gives you the volume charge density. Three-dimensional Dirac delta function means like this way. Okay, so you are having, let's say, d3 of x, so it means delta of x, delta of y, and delta z. Let's write this as a vector here. Okay, got it? So this is how we define three-dimensional Dirac delta function. I have put actually r as a position vector, so you can write, let's say, if I write this way, so it means delta of x, delta of y, delta of z. This is how we define it. I will not put explicitly 3 here. Okay, so it means this is a three-dimensional Dirac delta function. Clear? So this is how we define the charge density, okay, of the point charge distribution. So if I write now total charge, let's write rho integrate over volume V. So what you will get, summation over I Qi integrate over volume V. So delta R minus Ri. Okay, because this is the integration over volume, it's a three-dimensional Dirac delta function, it's equal to identity. So it is I, QI. What it gives me? Clear? So now let's go to this thing. So you are having this small amount of charge GQS rho dV. Yes? Yes, any question? So what I can do, okay, I need a 4 vector. Let me write dq multiplied by some dx mu. Okay? Okay, I'm just, okay, let's take the amount of charge dq in certain volume dv. Okay? So this is an invariant quantity. This is also what? Invariant quantity. Now what I am doing? Okay, I am trying to figure out what is the current density. Okay? In the 4-dimensional form. Okay? So for that matter, I need actually a 4 vector. Okay? Constructed out of these charges and so on. Okay? So now let's try to construct that kind of 4 vector. You are having dq, that's multiplied by dx mu. So I will write rho dv dx mu. Okay? Clear? Okay. So can I write it this way? dv dt dx mu by dt. Can I write it? Can I write it? Okay. So now let's look at this very object. dq dx mu. So how this will transform under Lorentz transformation? Since dq is a scalar quantity and this is a vector, so that means left hand side is a 4 vector. Okay? So this is simply what? A 4 vector. Is that true? Is it true or not? Okay. Now let's look at this dv dt. Let's look at this dv dt. If I multiply this very object, okay, so look at this very dv dt. So I can put it in this fashion. So 1 by c times c dt dv. Can I write it? Can I write it? Okay, so what this object is? 1 by c d4 of x. Is it true? So that means this very object is invariant under what? Lorentz transformations. So that means this object is a scalar quantity if I multiply it by c. Okay, let me write it. That's multiplied by c. So you are having 1 by c, okay, c dt dv, okay. Then you are having this rho dx mu by dt, okay. So this I can write 1 by c d4 of x. Let's say d dx mu dt. Clear? Clear till this point? Now look here. So the left hand side transforms as a Lorentz 4 vector. Is it? Okay, now this very object, this is a scalar quantity under Lorentz transformation. That means, okay, if left hand side is equal to right hand side, the transformation properties of left hand side must be same as what? Transformation properties of right hand side. It means this must transform as a 4 vector. This entire object. Rho multiplied by dx mu by dt. Clear? So, so much more because, okay, you know this rho changes under transformation, is it? So rho changes, this also changes under Lorentz transformation. It means this very entire object must be a 4 vector. So that means this 4 vector. So you are having 4 vector on left hand side and 4 vector on right hand side. Clear? So that means we have identified actually a 4 vector here. Okay, so this 4, okay, this I know, and now I have identified a new 4 vector here. Okay, so let's write it what exactly this 4 vector is. Okay, so let's write a 4 vector, this thing. Let's call that as j mu rho dx mu by dt. Okay, so this is known as current 4 vector. Okay, so let's look at whether it gives us the current or not. Okay, let's look at it. So let's take J0 when you are having mu is equal to 0. Let's take mu is equal to 0. So what you are having? So rho dx0 by dt. So what is x0? It is ct. So it is rho dct by dt. So what is that equal to? C times rho. What is rho? It is the charge density. Clear? So that means zero component of this 4 current density is the charge density multiplied by the velocity of light. Okay, in units of velocity of light. Okay, let's take this mu is equal to I. We're going from 1, 2, 3. Okay, so it is ji. So what it gives me? Rho dxi by dt. What is dxi by dt? Anybody? It's velocity. Because this is a 3 vector. Eh? So it is gx by dt means vx. Is it? dy by dt vy, dz by dt is vz. Okay. So that means it's vi. In other words, I can write this j vector as rho va. Now tell me what this is. Rho multiplied by the velocity. It's the current density. Is it? Is that true? So rho multiplied by velocity gives you the current density. So that's why we call this as a current density 4 vector. So it means the J0 and Ji components, okay, let me write it. This J mu is equal to J0 and let's say vector J. Okay, so if I write now this down indices, so it will be like this objective. Clear? So these components will transform in the same way as X and T are transforming under Lorentz transformation. Clear? Samajh aa? Okay. So now let's write this interaction term. Yes, any question? So what is our SI? X equal to minus E by C integral A mu dx mu. Clear? Okay. We wrote ERC, ERQ. No, I mean we are writing E, is it? Not Q. Okay, so here I have written actually Q in this very thing. So, okay, now tell me you are having E as the total charge. Okay, so let me write Q instead of E. Let me write Q. Let me write this Q as the total charge. Okay, let's write Q as the total charge. How I can write it? So can I write it minus 1 by C integral A mu dx mu, okay, times Q. Can I write it? Because it's a number, I can take it within the integration, is it? Can I take it? Okay. Now tell me how I can write this Q, total charge, in terms of the charge density. Can I write it in this fashion? dV times rho. Can I write it? Okay. So therefore I can write it minus 1 by C A mu dx mu integration over volume rho. Clear? Clear? So can I write it like this thing, minus 1 by C integration over A mu, okay, dx mu, okay, let me write it C dt, okay, multiply C dt, okay, then you are having this dV, then you are having rho. Can I write it? Can I write it? Huh? Okay, now look here, this very integral is actually along what? Actually the proper time. Okay, the parameter for the trajectory is the proper time, is it? So it's along this dx. Is it clear? So it's along the world line. Okay, now what I have done, I am actually converting this line, this is a line integral. I am converting this line integral into the 4-dimensional integral. Samajh aa? Clear? Okay, so I can write it in this fashion, minus 1 by C square integration C dt dV, like this very objective, and then you are having A mu rho dx mu by dt. Clear? So what is this equal to? So this is equal to d, okay, 1 by C square d4 of x, okay, A mu. What this rho dx mu by dt is? It is G. Clear? So now this is a 4-dimensional integral. Okay? So therefore I can write the total action. Okay. Let's write now the total action. So it is S is equal to, now if you are having, okay, for a single particle you are having minus mc over gs. Is that true? So this was for what? A given particle. Now I will consider many particles, some or all particles. Let's consider the many particles that are interacting with the electromagnetic field. So this term will form what? The action of all those particles. Clear? Then you are having the action corresponding to what? Interaction between the two things. So what is that? Minus 1 by c square integral d4 of x a mu and j mu. Okay? Clear? Okay, so this is the interaction term. Okay, so this means free particles. So this is the interaction. And then what you are having for the field, minus 1 by 16 pi c integration over volume. So let's call this as the volume omega d4 of x. Then you are having this f mu. Okay, so this is the free field. So this action governs all the classical electrodynamics. Okay. So this is the action for your classical electrodynamics. All the classical electrodynamics can be derived from this very equation. Clear? From this very action. Any question? Yes? Okay, so let me write it. Okay, so you can put it in this fashion. Okay, in terms of an integral, let's say integration s is equal to integration d4 of x, some Lagrangian L. Okay, so let's write this Lagrangian. So what that will be? Can you tell me what is the Lagrangian? It will be minus mc, sum over all particles, integral gt root of, what is that? 1 minus, is it? Okay, mc square. Minus sum over all particles. So then you have integration over. So I should not write integration. Okay, let me write it. Okay, so it is minus mc square root of 1 minus d square by c square. So here it means you need to actually count it to where? You need to take it to the four-dimensional form. Okay? But this is not useful to us, this very term. Then you are having minus 1 by c. Okay, so you are having this a, like j mu, a mu in this fashion. Okay, then you are having minus 1 by 16 pi c. So this is these two terms are actually useful to us. Why? Because these two terms contain fields. Now we will be doing entirely fields, not the particles. Clear? So in these two terms you are having fields. So this term does not contain any electromagnetic field. This is simply for the particles, okay? So this term contains field A, this also contains a field, okay? Clear? Any question? So now let's calculate the equation of motion. I mean to say, let's calculate the Maxwell's equations from here. Because if I know the action, I should be able to figure out what? Maxwell's equation, clear? So let's try to derive the Maxwell's equations. Okay. Okay. So I forgot to mention. So you are having two types of Maxwell's equations. If you look carefully, the Gauss law for electrostatics, it contains a source term, charge. Is it? Is that true? Gauss law for magnetostatics does not contain source term. It is source free, is it? So you can call electrostatic law, Gauss law for electrostatics, as the inhomogeneous Maxwell equation, and the Gauss law for magnetostatics as homogeneous because it does not contain a source term. Now look at the Faraday's law. It does not contain source. There is no source. It's only fields are changing. You don't have a source. So you can take Faraday's laws as homogeneous Maxwell's equation. Now if you look at the Ampere Maxwell's law, there is a source term J, current density, is it? So that means that is also now Maxwell's inhomogeneous equations. So these four equations now split into two groups. One are what? Homogeneous, another are inhomogeneous. Inhomogeneous equations contain source terms. Charges and currents are source now. Okay? Clear? Okay. So how to do the Maxwell's equations? I need to vary the action, is it? Samashaman? Okay, now look here. If I need to figure out, since Maxwell's equations relate fields, okay, in the homogeneous terms, they are only the fields, and in the inhomogeneous terms, you are having the sources, is it? So if you look here at this very action or this Lagrangian, so this is the purely field, is it? And this contains actually the source term. You are having a current density. Current density is now a source. Is that true? So that means if I try to figure out the Maxwell's equation from this very Lagrangian or from this very action, I need to actually vary this part of the action, is it? So since this does not contain any property of the field, its variation over the field variable will be 0. Okay? So that's why I will require only. Okay? So I will take only action which is necessary for me as this thing, d4 of x, okay, minus 1 by c square g mu a mu minus 1 by 16 pi c f mu. Okay? So this is the action I will consider to arrive at Maxwell's equations. Clear? So what I do, okay, I will take A's are fields, are independent, all A's. So all A's means what? A contains 4 terms, is it? Phi, AX, AY and AZ. Is that true? So all are independent of each other. Rather I should say linearly independent. And second thing, so these are the assumptions. Fields vanishes at boundary. Because we consider boundary in such a way that there are no sources. Okay, there are no charges and currents at the boundaries and the fields vanish at the boundary. Now let's look, is it a plausible argument? What is the electric field due to a point charge at certain distance r? It's 1 by r square. Now let's say if I move towards the boundary, I mean if I extend r to infinity, what will happen to the this field? It will drop to 0. Okay? So that means it's a plausible argument. So this is the main, boundary condition when we try to derive the equations of motion for any kind of field, okay, except the gravity. Okay, forget about gravity. All other fields we consider just the field vanishes at the boundary. Okay. Okay. At least in the electrodynamics we do it in this way. Okay. Okay, so let's, so our field is what? A, is it? A is our electromagnetic field. So that means I need to vary this action with respect to A. Samajh aavan? Okay, how to do it? So let's put the variation in action. So this is the variational principle. If you have any question to them, you can ask. Let's write. So what is our action? So let's write this delta S. So it will be integral d4 of x. So it's over some volume omega. Okay. Instead I will write this d4x as d omega. Can I write? Shall I write that notation? No. Okay, because I need to use 4 all the time. I'll use this as d omega. D omega means 4 volume element, okay? Clear? So D omega means what? 4 volume element here. Okay, this D omega can be larger space as well. So, samajh aavan? This is simply the notation, nothing more than that. So I have now minus 1 by c square, variation of this j mu, and then this e mu, okay? And then minus 1 by 16 pi c, variation of this f mu nu, f mu, okay? And this variation is equal to 0. I will put it at the end. Now let's look here. These sources are independent of the fields, is it? Is that true? Sources does not contain fields. They are independent of these things. So because we are taking the variation with respect to field, so it means this variation will not affect J. Okay, so it means omega d omega minus 1 by c square. So I will simply write J mu delta A mu like this way. Okay, minus 1 by 16 pi c. Okay, now let's write it. Okay, let me. So this is actually twice. Okay, I will show it. This object is twice. Okay, 2 times. Okay, I will show it. I will show it. Okay. So it is 2 times f mu nu delta. Okay, so let me write it. What is the variation of this object? Let me show it. Okay. So you are having variation of delta f mu nu, f mu nu. So how I write it? So it is delta f mu nu like this way, the product rule plus f mu nu delta. Clear? Okay, now I can raise these indices, 2 indices up and lower down these 2 indices. Can I write it? So it is delta f mu nu, f mu nu plus, so what I write? Okay. Let me write this way. So you raise these 2 things up, f mu nu, and then lower down these 2 indices. It is the same thing, is it? So the contracted indices, if you are having, you can raise them up and down, okay? Okay, you can raise lower to up and then upper to lower, okay? So it's like this thing, delta f. So what that is equal to? Twice f mu nu delta f. Clear? Clear? Okay. So you are having this twice f mu nu. Now what is this delta? So it is, what is this f mu nu? Partial mu a nu minus partial mu a nu. Clear? True? Okay. So I can write it twice f mu nu. Okay. So let's write partial mu variation in a nu minus partial mu variation in. Okay. So that's equal to, let's try multiply the 2, f mu nu partial mu variation in a nu, okay, then you are minus f mu nu partial mu delta. Clear? Okay, now what I can do, can I interchange the 2 indices here? So since mu is a dim index, is it? Mu is a dim index, mu is a dim index. Can I do it like this way? F nu mu and do the same thing here? Can I write it? Is there any problem? I am just replaced. Okay, you can write it, let's say alpha beta. Let me write alpha beta, okay? So then once you write it in terms of the alpha beta, so alpha I can put as nu, beta I can put as mu. Can I write it? You got it? So so I can simply write it as f nu mu partial nu delta a mu minus f mu nu partial mu delta. So I interchange it in this case mu with mu. Okay, because they are dim indices. So now I can use the anti-symmetry property of this f. Okay, so let's use the anti-symmetry property of this f. So it's f mu minus times f mu nu. Okay, now look here. When I use this as minus f mu nu, this very objective, you are having this minus F mu nu, partial nu this thing, minus times the same term. So it's twice. Okay, so I can put it as minus, okay, so 2 rules are 4, F mu nu partial delta. Okay, so that means this variation in F mu nu is this vector. Okay, so therefore I can write so therefore I write this delta S, it is equal to integration volume omega, then you are having minus 1 by c square J mu variation A mu. Okay, so you are having, okay, so it's 4, so it's 8, is it? Minus, so it's plus 1 by 8 by c F mu nu partial. Clear? समझ आवा? True? Okay, now what I will do, okay, look here, this delta A mu is free, is it? Now this delta A mu is where? In this very object, clear? So I need to integrate this very term by parts. Okay? So now whenever you encounter these kind of terms, just convert this to a total derivative. I will show you how. Okay? What does that mean? Okay? So let's look at this very term. Let's look at this very term. So you are having this F mu nu, okay, partial nu delta A mu. Is that true? So this is the term I need to evaluate. What I will do, okay, let me write. So I will write partial nu this way. F mu nu delta A mu. Okay, so let's write this derivative term. Is this a total derivative? So this is the differentiation of this entire object. Forget about this partial, this object and this object, this entire object. So now tell me how it looks like. So it's partial nu F mu nu like this way, delta A mu. Just okay, understand? So then you are having this F mu nu partial nu variation in this A. Is it? So that means you have arrived at which term? The term which you require. Is it? Is it true? Clear? So it is the same thing when I do the integration by parts, because sometimes the integration of parts is it becomes difficult, complicated in a sense, because you need a lot of terms. I mean to say, sometimes it becomes difficult what kind of measure I will put it. So just put it in terms of the total derivative, then it becomes clear. Okay, it does not become clear when you do. It is actually the integration by parts you are doing some term. Clear? Okay, now let's write that very term. Therefore, this F mu nu partial nu delta A mu, that's equal to this total derivative F mu nu delta A mu okay minus partial nu F mu nu delta A. Clear? Clear till this point? I think we have missed a factor. Have we missed a factor? Now like you are having 4 here, is it? There was 16, is it? So 4, 4, 16. So it is 4 by C. Clear? Okay, now so let's integrate this very object. So integrate this over volume. So d omega F mu nu partial nu variation in A mu. Okay, so now I'm integrating this object over volume because it is this very term, is it? So this is the integration over volume. Clear? Okay, so that's equal to integration over volume d omega partial nu F mu nu delta A mu minus integration over volume d omega partial nu F mu nu. Okay, now if you look, this delta A mu is now free. Is it? Isn't it now? If you see, isn't it the integration by parts of this very object? Is this the integration by parts? Is this the integration by parts? Just look. So what is the, you to put the total derivative and integrate total derivative of this object and integrate, and then the differentiation of the first quantity and then the integration of the other quantity. Is it clear? Okay. So now let's look at this very term, what exactly this term is. Okay, let's look at this very term carefully. So this term we call as a surface term. Huh? This is very important term. Okay, but here it's not important. We can throw it away. Okay, it is like this thing. Okay, just look here. So if you see this mu index is contracted, is it? If you see mu is contracted, is it? Forget about this partial mu. What is the rank of this object? 1. Okay, forget about this partial mu. So what is the rank of this very object, entire object? It's 1, because free index is only nu. Mu is not a free index. Okay, so that means this entire object is a vector. So samajh aawa? So you are having a vector, and then there you are in nu is contracted. So it means simply the divergence. It's like this thing. Okay, let's go. So you are having the volume integral dv divergence of some vector field v. Is it? Okay? Is this true? Now let's apply the Gauss divergence theorem. Okay, let's look, forget about that very. Let's apply the Gauss divergence theorem here. Okay, so what I will get? So I will be taking the closed surface, let's call that as S, then you are having v dot ds. So that means there is a dot product between the surface you are choosing and the vector itself. Clear? Now let's assume if this, okay, let's assume this v vanishes at boundary, okay? Let's assume v vanishes at boundary, okay? Okay, let's make that kind of assumption. If I stretch this surface to the boundary, what will happen to this integral? It becomes 0 because I am stretching my surface to the infinity, okay, or to the boundary. I am stretching it. At that very point, this v is what? 0. So that means it will become 0 at boundary, where I am assuming this v to be 0. So it means this very term will vanish where? At the boundary. Got it? So if you see, this is actually the total derivative. In other words, this is actually the total derivative of v. Is it true? Okay, let's forget that. Okay, let's take that very term. Okay. Okay, before doing that, let's move to the four-dimensional form of this very theorem. A simple generalization of this very theorem. So when you are taking it to the 4 dimensions, let's call that 4-dimensional volume to what? D omega. Clear? So how I will write this divergence? Can I write this as a divergence? Can I write it? Is this a divergence? Is this, first term, is this divergence? Just raise hands. How many of you say it is divergence and how many say it is not divergence? Is it divergence? First tell me. Yes or no? Yeah. Yes. Okay. So it's a divergence. Clear? So let's call the volume as omega. Now let's convert it to the surface integral. So you will be having a surface. Okay. If you are having a volume omega, its partial derivative gives me what? The surface. Okay. Let's take, if you are having volume, V is equal to 4 by 3 pi r cube. What is this dV? 4 pi r square. Is that true? So it means it gives you the surface. Okay. So now tell me what I need to construct. Now I need to construct the surface element. Is it? ds, this was defined in the 3-dimensional volume. Okay. So for first, what I need to do? I will write this vector field as such, v mu, and then multiply by some surface. Let's call that surface again as S. Okay, but I will put an index here. If you see, this is actually the dot product between two vectors, is it? So is this a dot product between two vectors? Is this a dot product? Okay, good. So this is the dot product. Now this surface is not same as this very surface. We call this as a surface hypersurface. Okay, now let's think in four-dimensional space-time. You are having three special coordinates and one time coordinate. Now if I choose my surface, x naught is equal to constant. X naught is time, is it? Let's choose the surface, okay, one of the surface to be a t is equal to constant. What that means? Where t is constant? Okay, let's think, okay, take the three-dimensional case. So if I choose, let's say, x is equal to constant, what plane is that? YZ plane, is it? Now if I am choosing in four dimensions, t plane is constant, what will be that? XYZ is the volume, or XYZ will be the surface, is it? So summation in four-dimensional surface, it will be actually what? XYZ. That means it will be simply 3 volume. So summation volume and element in simple three-dimensional space. Clear? Now if I choose x to be constant, what it will give me? It will give me the volume, but which contains coordinates t, y, and z. So summation. So in that sense, I call that t equal to constant to be the hypersurface, or sometimes hyperplane. We will call this as a hypersurface. So summation. So this very surface element is defined where? On this surface. Okay. So this is an element of surface here on this partial omega. Clear? So summation. Okay. So now if my field goes vanishes at boundary, that means this very term will be 0 where? At the boundary. So summation. Okay. So now let's take this very objective. Okay. So I am having this very object omega. So this is actually the four-dimensional form of the Gauss divergence. Okay. So d omega partial nu f mu nu delta e. Okay. So if you see, forget about this nu. So this is simply a vector. Is this a vector? Because mu is contracted. How many indices are there? Only one index nu. So that means this behaves. Okay, let's call this very object some f nu. Okay. So it means this. Okay, let me write this object. So let's define this very object as f nu. So it's simply as d omega partial nu f nu. Clear? So let's apply the Gauss divergence theorem. So it will be over some surface partial omega and some f nu. Okay, then let's write some surface. You put an index now here. Clear? Got it? Got it? Huh? Okay, let's put no issues. It's at a variable. Clear? So what is this ds? It is the hypersurface element. Okay. So what I will write actually now, what it is f? What is f? F mu nu delta a mu. So it is dx mu. Clear? Now look, all indices are contracted. Is it true? So now if I stretch my surface, okay, so this is a closed surface. So if I stretch my surface to the infinity, is it? So if I increase the surface, so what will happen? I will reach to the boundary. At the boundaries, field vanishes, is it? So it means this will go to 0 at boundary. Because if you see, this is actually the total derivative. This is evaluated at the boundaries. Okay, you need to evaluate this very integral at the boundaries. That's why we are evaluating this at the boundary. It's like this thing. If you so simple when we were doing the action for the free particle, you remember it? So how we define it? So you are having this delta s is equal to, there was one term, let's say p, then there was this delta x, evaluated at where? A and b minus then there was the other terms. You remember it? You remember it? So there were these terms. So then you said this, you want us to integrate by parts, if you remember. Then you say this, there is no variation at the endpoints, okay? So in other words, this vanishes at the boundary, this very term. Got it? So it was like this thing, Okay, so you need to, it was actually like this thing. So you are having this partial L, okay, let me write that. So there was actually partial L by partial Q dot and delta Q dot. Is that true? So it is something, okay, you write it in this fashion, d by dt of partial L by partial Q dot and then delta Q minus, okay, d by dt of partial L by partial Q dot multiplied by delta Q. It was like this thing. Once you then integrated it, so you are actually integrating this by parts. Is that true? So this is actually the boundary term. Huh? You integrate this thing, so this will cancel. This is the term which vanishes at the boundary. Okay? Similarly, now you are having this as the same thing. You are evaluating it actually on the boundary. So that's why it vanishes there. Huh? So it means this very term goes to 0 at boundary. Okay? So therefore, I will write again this thing. So you are having this delta S is equal to omega. So minus 1 by C square G mu delta A mu. Then you are plus 4 pi by C. Okay, for this object you are having this quantity with a minus sign. So you are having minus partial mu F mu. Then you are having delta. So this is equal to 0. Clear? So you can write it. Now let's take 1 by C will minus 1 by C will take out. Minus 1 by C, you take it out. Then you are having d omega, like this thing. So you are having 1 by C, J mu, delta A. Okay, let's okay, plus 1 by 4 pi. Okay, partial mu and mu. This is equal to 0. So it means this very object is equal to 0. So it means partial mu minus 4. Clear? Is it true? So so you can integrate the indices on partial mu F mu is equal to, because it will yield me a minus chain, so it will be 4 by G. Okay? So or in, let's write, because this mu, okay, nu is a domain index, mu is a free index, I will replace these two. Okay, so or I will write like this, partial mu F mu, so this is same 4 by C. These two equations are same. Just rearrange the indices, so they are the same. Okay? So this is, okay, now if you look here, you are having a source term here, is it? So that means, okay, these equations are Maxwell's inhomogeneous equations. Okay, we'll show it. We'll see. Okay, so these are Maxwell's inhomogeneous equations. Where are the Maxwell's homogeneous terms? So there is another way to derive those equations. Okay? So let's check it whether they really are Maxwell's inhomogeneous equations or not. Okay? So let's check it. So let's take rest to 0. Because mu is a free index in this very equation. How many equations are there? First tell me. Mu is a contracted index. Only index is what? Nu. How many values for nu? 4 values. 0, 1, 2 and 3. So how many equations are there? 4 equations. So let's take nu is equal to 0. Okay? So I am having that partial mu F mu 0 is equal to 4 pi by C J0. So we have written, okay, what is the J mu? It was 0 and vector J. Is that true? So what is this object equal to? 4 pi by C. What is J0? C times rho. What is that equal to? 4 pi rho. Then you should be able to guess what this equation yielded me. Right hand side I have arrived at 4 pi rho. It is Gauss law, is it? So it should give me the Gauss law. Now then, if you see, it's actually the divergence of f, is it? The divergence with respect to mu. So much more? Okay, now let's write it. So it is partial 0 f0 0 plus partial 1 f1 0 plus partial 2 f2 0 plus partial 3 f3 0, and that is equal to this way. Okay, so now what is f0 0? It is 0. What is f1 0? It's ex. Is that true? So it is partial 1, okay, e1. Okay, let's write. So in other words, I can write partial x, ex, plus partial y, ey, plus partial z, ez. So what is that equal to? 4 pi rho. What is that equal to? Del dot E, that's equal to 4 pi. Okay? So what is this? Gauss divergence law for electrostatics. Okay? Now let's take nu is equal to I. Nu is equal to I, and I is equal to 1, 2, 3. So you are having partial mu f mu I, that's equal to 4 pi c j I. Okay? So now let's write it. So there is a sum. So it's partial 0 f0 I plus partial, let's write partial j f j I, and there is a sum over j. Sum over j, that's equal to 4 pi by c j I. So what is f0 I? Okay, okay, f10 I have written as ex, is it? Or fi0 is ei. What is f0 I? Minus ei. Okay, so it is something, okay, it's 1 by c, okay, partial by partial t, okay, minus ei. Okay, then anybody? What is this partial j? Okay, what is this fji? Yes, so it's epsilon ji, let's write k bk. You sure? It's equal to 4 pi by c ji. So what is this equal to? So if you see, so it's minus 1 by c partial ei by partial t, okay, plus epsilon j I k partial j b k, it's equal to 4 pi by c j I. Now what is this object equal to? It's curl of b. It's which element? J and k. So it's ith element. Okay? So samajh aa? So rather I should put I here because I is here. Okay? So in other words, it's what? So curl of b. Okay, then you are having, you put it on the other hand side. So it's 1 by c partial e by partial t plus 4 pi by c g. Okay? Samajh aa? So you can take 4 pi out. So this is equal to 4 pi out. So what that is equal to? Let's write this one. G. Anybody? So when I take 1 by c out, what happens? 4 by c out. 1 divided by 4 pi. So what is this equation? Ampere Maxwell's law. It is again the inhomogeneous differential equation. Is it? True? Clear? Yes. So now okay. So this gives me two differential equations, two Maxwell's equations. Clear? So this very represents the inhomogeneous part of the Maxwell's equation. Now how to write the homogeneous part of the Maxwell's equations? Okay, let me write them. Let me go slowly. Okay, so you are having this f, right? F mu nu as partial mu a nu minus partial mu a nu. Let's write this thing. So this is our field tensor. Let's differentiate this by, okay, this way. Partial sigma. Okay, sigma again takes values from 0 to 3. Okay, mu nu. So it's something. Partial sigma partial mu a nu minus partial sigma partial mu a nu. Clear? So I'm just differentiating it. Okay. Now let's interchange the indices cyclic. in the cyclic order of this very equation. Okay, so let's call this as equation 1. Okay, interchange in a cyclic order. Let's take cyclic order. Interchange indices in a cyclic fashion. Okay. Now what is the cyclic order? I will just take mu here, then it will be nu, then you put sigma at the end. Okay. So look here, it is 1, 2, 3. Now what will be the another? 2, 3, 1. Clear? So summation. So this configuration is what? 1, 2. What is the another configuration? 2, 3. So this is cyclic configuration. So it will be something partial mu f nu sigma. What is that here? Now tell me what it will be. Okay, in this case it will be partial mu. Okay, partial mu a sigma. Is that true? Now in this case what it will be? Now tell me. Okay, mu is replaced by nu, is it? So summation here, if you see mu, okay, here it was mu, it is replaced by what? Nu. And sigma is replaced by, okay, let's look at sigma is replaced by what? Mu. So you are having sigma, you replace it by mu. Then you are having nu, you replace it by, you are having nu, okay, you are having nu, you are replacing it by sigma, like this thing. Then you are having nu, you replace it by nu. So much over? Okay, call this as equation 2nd. Okay, now what is the another combination? 3, 1, 2. Okay, so what is 3? Nu is 3, so it is partial nu f sigma mu. Is it true? So now look here in this very equation, what has happened? Okay, so this will go as, the first term will go as it is nu partial sigma e mu. Is that true? Now look at the other term is something weird. Okay, you are having mu and mu is replaced by nu, so it is nu. Then you are having sigma, sigma is replaced by mu. Okay, then this is replaced by sigma. Okay, add. So if I add, now look here, this very term, partial sigma, partial mu, a nu. Partial sigma, partial mu, a nu. Okay, so this term cancels with this thing because I can change it. I can write it partial sigma, partial mu. Okay, these are the partial derivatives, a nu. Okay, then now let's look at this very term, partial sigma, partial mu, a mu. Partial sigma, partial mu, a mu. So this is the term which cancels. Okay, then this term cancels with this term. So what you are having? So you are having partial sigma f mu nu plus partial mu f mu sigma, partial mu f sigma is equal to 0. So this is known as Bianchi identity. Okay, and this represents Maxwell's homogeneous equations. Homogeneous. Two homogeneous equations come from this. Okay, let's put it in a simpler form. Okay, so let's put it in the simpler form. So you need to do these things at your place because there are holidays coming. Okay. So let me define a quantity. What is known as the dual tensor? So you are having f mu nu. Let's calculate it as dual tensor. What does? Okay, I will write it in this fashion. So you are having f mu nu. So write it as half a mu nu alpha beta f alpha beta. So this is how. So this object is dual to what? F mu nu. Okay. In this case, in this f mu nu, okay. So e's are replaced by minus e's. It is like this. So while you are having entries of E, you replace them by what? B. Okay? And while you are having entries of B, you replace them by what? E. So you have entries of E and B. E arise on the 0 like this thing, first row and first column. Is that true in this F? And B's are the other elements. Now if you write the dual tensor, the first row and the first column will be B and the other elements will be what? E. So this is how we define the dual tensor. Clear? So you can check it. Now let's check it whether I am saying true or not. Let's take f01. Okay, f00 is 0. Let's take f01. So it will be 0, 1 here, is it? So what you are having then? Alpha and beta, is it? So if this is 0, 1, what are the possible values of this alpha and beta which will give non-zero? 0, 1, 2 and 3, is it? And 3, 2. Okay, if I take, so these are the only non-zero values. Let's take this way. So I will be having 0, 1, alpha, beta. Okay, now let's try. So you will be having alpha goes from 0 to 3, beta goes from 0 to 3. If I put 0, then you are having two same indices. If I put 1, 2 same indices, then this alpha should be what? 2. Or it should be 3. Beta should be also what? 2 or 3. So it will be like this thing. Half of epsilon 0, 1, 2, 3, 2, 3 plus, okay, epsilon 0, 3, 2, okay, 3, 2. Got it? So what it will give me? What is F23? So this is 1. Okay, half of. So epsilon 0, 1, 2, 3 is 1, is it? So what about this thing? So it is F23 minus, this is minus 1 because your two indices are interchanging, F32. So what that is equal to? You can interchange 2 and 3. So it is half of F23 plus F23. So what is that equal to? Simply F23. Now tell me what is F23? It's minus B. It is minus BX. Okay? So what is F01? So sorry, it is BX and this is what? Minus EX, is it? So that means EX is replaced by what? Okay, so you are having EX replaced by minus BX. So so E is replaced by minus B and B is replaced by minus C. Got it? So that means, so this F01 term will be simply equal to what? Minus B. No, so sorry. It will be simply B. Okay, so it F, because this F tilde, so this is in the dual tensor. So it will be simply BX. So it will be like this thing. F tilde mu, it will be like this objective. So first in these are 0, then you are in BX, BY and BZ. Okay, BX, BY and BZ. Then you are in 0. What it is? Minus B. So it will be what? Anybody? So it will be. So anybody? So it's minus EZ. So then you are in EY probably. Then you are in EZ. Okay, minus EZ. Minus. Okay. Sorry, EY. Then you are in 0. Then you are in EX. Just check it. Huh? So it will be like this. EX will be negative. EY was, I think, negative. Sorry, BY was negative. Huh? Is that true? So just check the signs here. Now what was here? If you remember, in F, you are having minus EX, minus EY, minus EZ. You remember it? In F, you are having 1 as minus EX, minus. Okay. So since it's anti-symmetric, it will be like this thing. Clear? Just check the signs. You will be having row and columns replaced by, sorry, first row and first column replaced by magnetic fields, and the other non-zero elements will be replaced by electric fields. Got it? Okay, so if I write it in this fashion, I can plug. So you simply multiply this epsilon. So I can write this thing as epsilon alpha beta mu partial. Okay, so I can simply write it this way. So this equations I can simply write it as partial mu f tilde mu. So these are homogeneous maxims. Okay? So समझ आवा? Okay? No? समझ आवा? You people followed it? Okay, let's check it out. Just one step. Huh? No, then I will leave. Okay. Okay, let's write. So you are having F mu nu. Let me write this way. Forget about this sigma for the time being. Let me write alpha sigma mu nu. Okay, partial sigma F mu nu, like this thing. So I am multiplying this alpha sigma mu nu. Okay, this entire thing. So it's again alpha sigma mu nu partial mu F mu sigma plus alpha sigma mu nu partial mu F sigma mu, that's equal to 0. Clear? So if you multiply with half as well, okay, let's multiply with half here. So now you are having epsilon alpha. Okay, so I can write it partial sigma half of epsilon alpha sigma mu nu F mu nu. Okay, so then I can write partial mu half of epsilon alpha sigma mu nu F mu sigma. Okay, plus partial mu half of epsilon alpha sigma mu nu F sigma mu, that's equal to 0. Now look here, what these objects represent? They are the dual tensors, is it? Okay, mu nu. Look at that. Alpha beta is contracted. This is a dual tensor, F tilde alpha sigma. So this is a dual tensor. Can anyone tell me? F tilde nu and sigma are contracted, alpha mu something, and this is a dual tensor, F tilde, okay, alpha nu. Is it? So solution? Clear? Okay, so you are having, okay, now let's write it. Partial sigma F tilde alpha sigma plus partial mu F tilde alpha mu plus partial mu F tilde alpha nu is equal to 0. Now if you see, sigma is contracted, is it? So are they all the same differential equations? Sorry, same kind of all things. I can replace this sigma by mu, nu by mu, is it? Because nu is a dummy variable. So it means these are how many terms? They are the identical terms, is it? Summation? So it means this is simply 3 times partial mu F tilde alpha mu is equal to 0, which implies what? Partial mu F tilde alpha mu is equal to 0. Clear? So these are the homogeneous part of the Maxwell's